factor analysis rather than component analysis. And I'm going to keep it on the normally distributed random data generation, so I'm going to keep that at 1. I prefer permutations of raw data, as I explained in the other video series on parallel analysis, but it takes too long for a video demonstration to actually calculate the Monte Carlo simulated eigenvalues. So I'm just going to use the number 1, which is normally distributed random generation of data for 5,000 samples. So I'm going to run that. It'll still take SPSS a few seconds to run this part of the analysis. And I think because Camtasia is running in the background, it's taking even a bit longer than it should normally. But that wasn't too bad. So the parallel analysis is going to give me the results in a scree plot. And as I demonstrated in the other video tutorial, I kind of change things up here so that I can actually see. And what we can see is that the scree plot's coming down, so that eigenvalue there definitely looks statistically significant, and these two as well. So it looks like there's definitely 3 statistically significant common factor eigenvalues. And then there's 2 over here that are just slightly above the competing Monte Carlo simulated eigenvalues. And this is where reality and subjectivity and instead of quantity, we're talking about qualitative, that's the word I'm looking for, qualitative considerations. And in my experience, when you analyze item level data, there's a lot of uninteresting common variants that aren't really factors. They're really just correlated residuals, 2 items that share more variance than they should because they have similar wording. So in my opinion and in my experience, these are not statistically significant eigenvalues representing true factors. It's just it's not noise, it's not random data, but it's just it's not significant enough variance to be actual factors. But these 3 here I would definitely feel confident in extracting. So based on this first step in the factor analysis, which is using the scree plot, I've determined, based on statistics as well as qualitative judgment, that there are 3 factors to extract. So I'm going to go into dimension reduction, factor, because I've done the analysis already. The variables in there, but it would normally look like this. So I've got my 20 items over here, and I'm going to take the 20 items and I'm going to put them into the variables box. I'm going to click descriptives, and what I've already got, usually it's yeah, you don't even get your coefficients. So I click on coefficients. I'm not that interested in significant levels at this stage. I've got the KML Bartlett's test of sphericity and the reproduced, and I think that that's probably the most people usually do, and I think that's probably a lot of people don't even look at the reproduced correlation matrix. I think you're going a bit far to look at the anti-image and inverse matrices, because nobody reports that. I haven't seen the anti-image correlation matrix reported anywhere, or anyone even referring to it. But I'll click it in for this demonstration. But typically I never use it, and I don't really see anyone else use it either. I think it's redundant with other information, like doing the parallel analysis. We know the parallel analysis is that we should extract 3 factors from the data, and there's other things we can look at to help us determine. Okay, so here's principal components is usually the default. I had it on maximum likelihood because that's how I looked at what I was going to do. But to do a factor analysis, you need to change that. And SPSS gives you several options, and they all have their own historical significance. But I would argue that maximum likelihood is probably the best estimation procedure. There are probably papers that you can find that would demonstrate that to be the case. I think these other procedures are here more from a historical perspective, because previously with computers in the 1980s and early 90s, they weren't very fast. They weren't fast enough to do maximum likelihood estimation, and so people were doing principal axis factoring and alpha factoring. But I think in today's day and age, you should feel comfortable doing a maximum likelihood estimation. People say that you need a larger sample size for that. I'm not so sure that's true. I think you need a large sample size for every type of data reduction analysis that you want to do. In this case here, I've got the scree plot checked because I want to see my scree plot, even though I've done the analysis already. I wouldn't normally check it if I've already done a parallel analysis. And then I'm going to extract. So based on eigenvalue greater than 1, do not use that rule. It's been criticized so often and does have some theoretical foundation.